Every branch of modern science, without exception, uses linear algebra. Statistics, data science, and artificial intelligence are all built on the foundations of linear algebra. If you want to do research in any of these areas, you have to master the topics that we discussed in this course. One of the main tools that is used in applications today is the machinery of eigenvectors and eigenvalues. Only the sizes of matrices that appear in modern applications often measure in thousands. Large matrix sizes poses a clear challenge to accurate computations of eigenvectors and eigenvalues. There is one case, however, where computing an eigenvalue and an eigenvector is fairly easy. Here we shall talk about the dominant eigenvalue and the dominant eigenvector. Let's give a definition. An eigenvalue lambda is called the dominant eigenvalue of a matrix A if for any other complex eigenvalue mu of matrix A, the following condition holds. The complex norm of mu is strictly less than the complex norm of lambda. And the dominant eigenvector is an eigenvector that corresponds to the dominant eigenvalue. We make the following important remark, that random real matrices are diagonalizable over complex numbers. This means the following, that if you have a matrix that is built with some experimental data, then you should expect that such a square matrix be diagonalizable over complex numbers. The reason for this is that if we consider a characteristic polynomial of this matrix, then the probability that this characteristic polynomial will have multiple roots is equal to 0. And if we have a characteristic polynomial without multiple roots, then we will have one eigenvector for each complex root of the characteristic polynomial. And this will yield diagonalization of the matrix. Of course, we should keep in mind that not every matrix comes from random data. And certainly, we will face situations where we have to deal with matrices that have inherently multiple roots of characteristic polynomials, and perhaps Jordan blocks. However, these are special situations, and if you have a fairly random matrix, then the expectation should be that this matrix is diagonalizable. Now, let us look at the diagonalizable case. So suppose V1 through Vn be the basis of Cn that consists of eigenvectors of A. We assume that these vectors exist but are unknown to us, and they are difficult to compute when n is large. Let U be a random non-zero vector in Cn. Let us expand U in this eigenbasis. So we write U as C1 V1 plus Cn Vn. Again, since the eigenvectors are not given to us, this is something that we cannot compute, but we can only state that this expansion exists. Now, what is the meaning of this word random? So here, random means that we assume that all these coefficients in these expansions are not equal to 0. If we pick a vector u at random in Cn, then the probability that all of these coefficients will be non-zero is 100%. Without loss of generality, let us assume that eigenvalue lambda 1 is dominant. So for all j from 2 to n, we will have that complex norm of lambda j is strictly less than the complex norm of lambda 1. Now, let us apply matrix A to this random vector u. Since we wrote u as this linear combination, the result will be C1 lambda 1 V1 plus C2 lambda 2 V2 plus Cn lambda n Vn. If we apply A again, then we will get that A squared u is equal to C1 lambda 1 squared V1 plus C2 lambda 2 squared V2 plus Cn lambda n squared Vn. And we continue this process. What we shall see is that because lambda 1 is the dominant eigenvalue, the coefficient at the vector V1 will grow faster than the coefficients of all other vectors in this expansion. Now, there is one numerical problem with this process. If the norm of lambda 1 is greater than 1, then the coefficient at V1 will go to infinity. And if the norm of lambda 1 is strictly less than 1, then all of these coefficients will go to 0. There is, of course, an easy way to correct the situation. So what we'll do is we will set that vector u1 is equal to u, and recursively we define a sequence of vectors where we say that uk plus 1 is equal to a applied to vector uk, and then we divide by the length of the vector auk, so that this ensures that for all j, the norm of our vector uj is equal to 1. Then it's easy to see that the limit when k goes to infinity of these vectors uk is going to be the dominant eigenvector v1, well, divided by its length. So we see that we have a very simple procedure for computing the dominant eigenvector. We just pick a random vector in our space and iteratively apply multiplication by our matrix and then normalizing the result after each step. This process will converge and we will obtain the dominant eigenvector. Applying matrix A to the dominant eigenvector, we will of course recover the dominant eigenvalue. The rate of convergence depends on the quotient of absolute value lambda 2 to absolute value lambda 1, where lambda 2 is a subdominant eigenvalue. That is the eigenvalue with the next largest complex norm. As an application of this idea, let us discuss the PageRank algorithm. This is the algorithm upon which the original Google search engine was built. Google was a relative latecomer in the area of search engines. Yet it quickly became the most popular search engine simply because it was built on better mathematical ideas and was able to deliver more accurate search results. Search engines try to match the keywords from the query to the keywords that appear on various web pages. Earlier search engines had a problem that their output was dominated by often insignificant websites that contained the right combination of keywords. In the early days of the internet, when the number of websites was fairly small, the ranking of important websites was done manually, and this was not an effective procedure and simply became unfeasible when the number of web pages exploded in late 1990s. And this is what Google did. Their PageRank algorithm was able to assess importance of web pages without any human input. The creators of Google, Sergey Brin and Larry Page, came up with the following model. Imagine a web server who starts at a random website and then randomly clicks on links moving from one website to another website, selecting on each page a new link to click on at random. Once in a while, the surfer gets bored and instead of clicking on a link at a page, will jump at a random different website. If that surfer also gets to a web page that has no outgoing links, then again the web surfer will jump to a new web page at random. The page rank of a given website is the probability that this random surfer will be on that particular web page at some specified point in faraway future. How can we calculate these probabilities? We construct the following matrix. Let n be the number of websites to rank. We construct an n by n matrix A with entries aij's, where aij is the probability that this random surfer will transition from website J to website I. So we indexed all websites by integers from 1 to n. Let d be the parameter that describes the probability of jumping to a random website instead of following a link. In the original paper, Brin and Page indicated that they chosen the value of 15% for this parameter. Let mj be the number of links outgoing from website J. If mj is equal to 0, then we choose aij to be 1 over n for all I. This means that if the website J has no outgoing links, then we jump at random to any other possible web page. If mj is not equal to 0 and there is no link from j to I, then aij is equal to d over n. If mij is not equal to 0, then with probability d, instead of following a link, we will jump to a random website, and this website could possibly be website I. And finally, if mj is not equal to 0 and there is a link from j to I, then aij is equal to d over n plus 1 minus d over mj. Of course, these numbers d over n are very small, and the values of coefficients aij will be much greater if there is a link from j to I. Matrix A is left stochastic. Which means that the sum of entries in each column is equal to 1. So for each j, the sum I goes from 1 to n of aij is equal to 1. And also, all coefficients aij are positive. Let us quote the following Perron-Frobenius theorem. Let A be a square real matrix with aij strictly greater than 0. Then A has a real dominant eigenvalue, lambda, which is positive, which means that for every other complex eigenvalue, mu of the matrix A, we have that complex norm of mu is strictly less than lambda. The eigenspace corresponding to lambda is one-dimensional. And there exists an eigenvector for lambda with all positive components. Here we are saying that up to a real scalar, there exists a unique dominant eigenvector. And this eigenvector will have all components of the same sign. So that is, we can choose it to have all positive components. If A is left stochastic, then this dominant eigenvalue is equal to 1. Perron-Frobenius theorem ensures that for the matrix A that was built in the PageRank algorithm, there exists a unique dominant eigenvector. And this dominant eigenvector can be computed using the procedure that we discussed. We can start with a vector that has all positive components. So, for example, it will have 1 over n in each component. And then we iteratively apply matrix A to this vector. Since the dominant eigenvalue is guaranteed to be 1, then we don't even need to renormalize our result. After several iterations of this procedure, and Google used something like 20 iterations of this process, we will get a vector which is very close to the dominant eigenvector. The components of the dominant eigenvector are the ranks that are assigned by PageRank algorithm to each website. If we renormalize the dominant eigenvector so that the sum of its components is equal to 1, then component I of this dominant eigenvector may be interpreted as the probability that this random surfer will be on web page I at some specified point in faraway future. This example shows how a simple idea from linear algebra helped to build a high-tech giant.